Swayam Prabha. Digital India. Educated India.
Welcome to lecture 57. In last lecture we were discussing about the design of transonic compressor, which was having expected pressure ratio of 1.63. We were having constraints with tip diameter, hub to tip ratio at the entry is given to us, speed it was limited by 16,100, and we started doing design with initial consideration of assuming certain parameters, and finally we have come up with the solution, say our axial velocity to be 225 meter per second, our peripheral speed to be 400 meter per second, tip diameter, that's what was coming 0.516, that's what is less than what we are supposed to be, and that's the reason why we have accepted with rotational speed it was coming 14,805, and tip Mach number which was constrained saying 1.4. In spite of that, for our assumed values of axial velocity and peripheral speed, that's what was coming 1.35, and that's what we have accepted with. Then we were discussing about the flow track configurations. So if you recall, this is what we were discussing in last lecture, where we have configured our say flow track for axial flow compressor. First, that's what is with say constant tip diameter configuration. In that, our tip diameter, that's what will be remains constant, and as we know our expected pressure ratio, that's what is in higher range 1.63, that's what is higher in that range. That means we will be having our exit configuration or exit dimensions to be different, because we are planning to have satisfaction of continuity equation. If we consider our pressure ratio to be higher, that means that's what will be giving our density also to be higher, and in order to maintain our axial velocity to be constant, our exit area, that's what was decreasing. And if we configure our requirement as a constant tip diameter, then my hub diameter, that's what will be changing compared to my entry condition and my exit condition. There is second configuration that is also possible, in which we will be maintaining our hub diameter to be constant. Now when we say our hub diameter to be constant, in order to satisfy the continuity equation, we will be having our flow passage, flow track, that's what will be looking like this, in which my tip diameter, that's what will be going to be decreased towards the exit of my stage. There is one more possibility in which we will be assuming some radius ratio, or maybe we will be configuring saying like maybe constant mean diameter kind of configuration. Then we will be having our passage to be converging passage like this. Now today we will be discussing in detail design using say constant hub diameter configuration. So in order to move with constant hub diameter configuration, very first thing, that's what we need to find, that is with the diameter ratio. So what we know, we have our continuity equation based on my mass flow rate equation, that's what we can write down saying like density into area into say axial velocity. This is what we are configuring at the exit. That's the reason why this is what is say rho 3 pi, this is what is my hub diameter, and this is what is my ratio, and into say axial velocity. Now as we have discussed, we have done our calculation for hub diameter and tip diameter earlier. For this configuration, we are assuming our hub diameter to be constant. That means my R1h and R3h, this is what will be remaining constant. and that's what is say 0.0967 meter. Now once we know this hub diameter, based on my continuity equation we can calculate what will be my say ratio of hub to tip, and that's what is coming 0.4363. Now here in this case, once we understand the dimensions for hub diameter, based on this ratio we can calculate what will be my tip diameter, and that's what is giving me my tip diameter to be 0.22 meter. So if we draw our passage, we can say this is what is my hub diameter and this is what is my tip diameter. Okay. Now once we have done this calculation for hub and tip diameter, we are looking for say what will be the dimensions at the mid station, because at mid station if we configure at station 2, my R2H, that's what will be say constant, and my R2T, that means my tip dimension at station 2, that's what we will be taking as an average value, and this is what is coming as a 0.24 meter. Now we can say we are having all the dimensions at entry, at mid station and at the exit. Now if this is what is known to us, what we know is we are planning to do our calculation, since this is what is high pressure ratio configuration and we know this is what is a transonic compressor, that means we need to do calculation for our mid station. And as we have discussed, when we will be having say subsonic compressor, we are considering our mid station at 50% of span, and when we are configuring or when we are considering our compressor as transonic compressor, all calculation that's what we are doing at 75% of span. So we can say this is what is our mid station. So at the entry we need to have value of radius, at mid station also we are looking for radius, and at the exit also we are looking for radius, because that's what will be giving me the streamlined pattern at 75% span. Okay, so if we configure in that direction, then we can say my mean radius at the entry, that's what is given by R1H plus 0.75. This is what is my tip radius minus hub radius. We can say this is coming say 0.217 meter. Same way at mid station also, at location 2 we can calculate, that's what is coming 0.204 meter, and at the exit that's what is coming 0.191 meter. Now this is what is must in sense of doing our calculation. We need to be very careful in considering and calculating this mean radius. Okay, so it is advisable based on what dimensions we are getting for hub and tip, just draw a diagram and based on that you just try to calculate this radius. Okay. Now this is what we can say in sense of the configuration what we have decided with our axial velocity of 225 meter per second and our peripheral speed, that's what we are writing as a 2 pi r n by 60. Here our rotational speed we have considered as 14,805 rpm. So this is what will be giving me dimensions at different stations, and we need to be very careful here at hub, at mid station and at the tip station. At location 1 we will be having u, that's what will be different. Same way for mid station also we will be having these dimensions to be different. And this is what is my station 3, basically that's what is the exit of stator. So that's what where we are not considering any peripheral speed configuration. So we need to be very careful in sense of doing our calculation for peripheral speeds. Let's try to look at what all are the changes. Suppose if we consider this is what is with our constant tip diameter, for which we have done our calculation, we have done our design, and these are the station 1, 2 and 3 for constant hub diameter. Let's try to compare what exactly will be the change, because this change that's what will be reflecting in our design. So if we configure, this is what is my mean station calculation, it says my entry mean station, that's what is 0.216, at mid station it is 0.226, and say at the exit we will be having 0.234. So we can say this is what is giving upward direction kind of configuration for the streamlines. Here these are the dimensions at hub, tip, at mean station. Suppose say if we are comparing these two numbers, we can see here at mid station we are having radius, that's what is same. At say mid station we are having, that's what is say 0.204. You can compare this value, it is 0.226 for constant tip, and for say constant hub configuration it is 0.204. At the exit also my mean radius, that's what is decreasing. So we can say our streamline direction, or if we draw the line that's what is connecting all this point, that's what is showing say the flow to be moving towards the hub direction. So that's what is the imaginary line, but we can realize, we can understand that part. Now what is happening, if we are configuring here, we can say my radius at the hub, at the exit, that's what is lower. At mid station, that's what is also we are having lower value, and at say our tip station, there also we are having this value coming to be lower. Now this is what all numbers we are looking at, that's what is basically reflecting on our peripheral speed. And we know our peripheral speed, that's what is a function of my radius. If we are having the change in this peripheral speed, accordingly we will be having change in flow velocity components. We also will be having change in flow angles. And if we are having this configuration, that's what is different, we can say what all say observation parameters like diffusion factor, degree of reaction, de Holler's factor, my deflection angle, my different flow angles, those all, that's what will be getting changed, or that's what will be having different values. There is a purpose specifically in one lecture, that's what is dedicated for this particular design, because that's what will be giving us the feeling of, suppose say if we will be configuring this kind of design. Okay, so let's move it what all we are discussing. Now here in this case, once we know what is our entry station, that's what we will be dividing into say 9 station. So if we configure my radius at the hub, that's what is 0.097, and this is what is at the tip, that's what is say 0.258. Be careful, we are always looking for R1, we are looking for R2, and we are looking for R3. If you recall, this is what is we are looking for the calculation of U. So make a habit of writing this R1 and R2 separately, even R3 also separately when you are doing your design for stator. Otherwise there are chances that you will be making mistake. Which radius to be selected, that's what is always very important. So this is what is at say 75% span, that's what is coming 0.217. Now here this is what is our design requirement. So we will be initiating our design at the mid station. Now if you recall, when we were discussing constant tip diameter configuration, we have initially assumed our total pressure, say delta P0, or say pressure ratio at the mid station, that's what we have initially assumed. And then after in later case, if you recall, we have changed our loading in order to set the loading both towards the tip as well as towards the hub region in order to receive expected pressure rise. So here also we can move it, say assuming our pressure ratio to be 1.63, and later on we can modify the total pressure ratio or expected pressure ratio as per the design. But in order to reduce the iteration, we are not doing like that. Let's assume our delta P0 at the mid station to be on the higher side. From initial only, we will be taking this as a 70,150 Pascal. Now this is what we are assuming at say delta P0 at the mid station. Now once this delta P0, that's what is known to us, we can calculate what will be our temperature rise, total temperature rise at the mid station, and this is what we are writing in terms of say polytropic efficiency, my entry temperature and delta P0 and total pressure at the entry, and that's what is coming say 52 Kelvin. Now basically this delta P0, that's what is very important, because in order to do the calculation at mid station we are looking for velocity components, we are looking for flow angles. So what we will be doing, we will be assuming our aerodynamic work and thermodynamic work, that's what is to be same, or we can say here we are writing Cp delta T0, that's what is say lambda into omega. Here we need to be very careful, say this radius, say when we were doing our design for subsonic compressor, that time we were writing that as a U2CW2 minus U1CW1, but here in this case say there U1 and U2, that's what our radius, that's what was coming to be say same, and that's the reason why we are putting U2CW2 minus U1CW1, but here in this case our radius, that's what is different, and that's the reason why we are writing as a R into omega minus R into omega at the entry station, and we will be putting this is what is say lambda into omega R CW2 minus R CW1. Be careful about when we are doing our calculation for say supersonic or say transonic compressor. Okay, we are assuming our entry condition to be axial, and that's the reason my whirl component we are assuming to be 0 meter per second, and that's what will be giving me my whirl velocity at the exit of my rotor, and that's what is coming 168.38 meter per second. Now this is what we realize. Now alpha 1, that's what is known to us, my peripheral speed is known to me, axial velocity is also known to us. For that we can do our calculation for say angles beta 1, beta 2, we can calculate what will be our absolute velocity at the entry, what will be our absolute velocity at the exit, my relative velocity at the entry and relative velocity at the exit. So this we are writing in sense, if we configure, this is what is say my entry velocity triangle, since this is what is my axial entry, so alpha 1, that's what is equal to 0. So from trigonometry we can say tan beta, that's what is given by u by Ca, and that's what is coming 56.26 degree. Now same way at the exit we can write down say tan beta, that's what is u minus Cw2 divided by this is what is my Ca, and that's what is giving my beta 2 at the mid station at the exit of rotor as 33.77 degree. Now once we are calculating our beta 1 and beta 2, we can calculate what will be our delta beta, and that's what is coming 22.9 degree. Okay, same way we can do our calculation for alpha at the exit. So alpha 2 at the exit, that's what is given by Cw2 by UA. These numbers are known to us, we can calculate our alpha 2, that's what is coming 36.81 degree. Now what we are looking for is observation for our degree of reaction at the mid station, and as we have discussed, this degree of reaction, that's what we are calculating as a 1 minus Cw2 plus Cw1 divided by 2u. Here in order to avoid the confusion, we will be taking say mean, or we can say average peripheral speed, and that's what is say 326.72 meter per second, that's what is giving degree of reaction as a 0.74. Now next component, that's what is of our interest, that's what is our relative velocity at the entry and relative velocity at the exit of the rotor. So from trigonometry, if we will be taking say cosine, say cos of beta 1, that's what is say Ca by relative velocity component V1, that's what is given say V1 as say 405.12 meter per second. Now same way we can do our calculation for relative velocity at the exit, and that's what is coming as a 269.4. You can say here we are having effective kind of diffusion, that's what is happening. My relative velocity at the entry is higher, my relative velocity at the exit, that's what is coming to be lower, and that's what we are calculating as a de Haulers factor, and that's what is coming say 0.66. Okay. Now next important parameter for us, that's what will be to decide with the number of blades and what will be the chord of my blade. So as we have discussed our aspect ratio in earlier design, that's what was coming say 1.6. So in order to compare these two designs in that sense, we will not be changing this aspect ratio. Let's take same aspect ratio here for constant tip diameter configuration. So aspect ratio I am taking as a 1.6. Now in order to calculate the height of my blade or the span of my blade, that's what we are doing as a h1 plus h2 by 2. So h1 and h2, that's what is given by r1 minus rh at entry and rt minus rh at the exit, and this is what is coming to be 0.167 meter. Based on that we will be calculating our chord, and that's what is coming as a 0.105 meter. Now if we compare this number with our earlier calculation with say constant tip diameter configuration, this chord was coming 0.09 meter. So you can say here our chord, that's what is coming to be larger. Okay, so the changes, that's what will start reflecting now. Same way in earlier design we have assumed our number of blades for the rotor as say 29, so we will not be changing those number of blades. Okay, so number of blades, that's what we have assumed to be 29, same we will be putting here, that's what will be giving us the pitch to be 0.046 meter. Now based on pitch and chord we can calculate our solidity, and that's what is coming as a 2.31. Once we know what is our solidity, my immediate parameter that need to be calculated, that's what is say my diffusion factor. So the diffusion factor of this rotor, that's what we can calculate based on beta 1, beta 2 and based on my what is the solidity. So if we are writing this, this is what is coming as say 0.44. Now in order to calculate my blade parameters, very first parameter which we need to calculate is say slope factor or say Carter's parameter, and that's what we are writing here. We are considering our say camber line, that's what is say circular arc camber line, and that's the reason my A by C, that's what we are taking as a 0.5, and my parameter or M factor, that's what is coming as a 0.343. Now once we know what is our parameter M, we can calculate our camber angle, that's what is delta beta minus incidence, and in the as a function of say my M parameter and solidity. So if we are doing this calculation, my camber angle at the mid station, that's what is coming 29.57 degree. Same way we can use our Carter's relation for calculation of deviation angle, and that's what is coming as 6.69, similar to what all we have discussed earlier for almost all design. Based on your computational study or based on your past experience, you can do the correction for your deviation angle. Same procedure we will be following here also, and we can do our camber angle correction, and we can do our calculation for say stagger angle correction. So these are the angles what we are getting in sense of 32.07, that's what is my corrected camber angle, and 40.21, that's what is my corrected stagger angle. Now in overall if we look at, this is what is my station. So if we configure here, as I was saying, we need to be very careful in sense of my radius. So this is what is my radius R1, and this is what is my radius r2, this is what is my radius r3, because that's what will be giving me u1 and u2 to be different. Okay, so based on that, this is what is a table, that's what we have prepared, assuming our delta P0 that to be here. Okay, now once this is what is we have done at the mid station, next step for us it is to calculate at hub station as well as at the tip station. So in order to do calculation at the hub station, we are following the approach, that's what is say our fundamental design approach. We need to assume delta P0 near the hub station, and we know hub is critical in sense of the having flow turning angle to be large, and it may be possible that my degree of reaction may be going lower in that region. So it may possible, like we have discussed earlier also, some of the portion near the hub region for this compressor may act like a turbine if we will not be configuring or if we are not designing properly, and that's what will lead to losses, maybe in sense of rise of pressure or maybe in sense of say my operating range, and that's the reason why we need to select this number iteratively. Okay, and in order to have that flexibility, we are having now our Excel sheet program with which we can do the modification what we are looking for. Say for design, here in this case we have assumed near the hub region going aggressively, we have taken this pressure ratio expected near the hub to be 1.5, and that's what is giving me my pressure rise near the hub to be 50,471 Pascal. Now once we have assumed this delta P0, we can do our calculation for delta T0 at the hub station, and that's what is coming 39.23 Kelvin. Now if we compare our aerodynamic work and thermodynamic work, we will be getting our work component. Be careful here also what we are discussing in sense of my R2 into CW2. Be careful about this design calculation, do not make any mistake here. That's what is giving me my work component at the hub to be 268.32 meter per second. Now once we know what is our axial velocity, our peripheral speed, one of the work component based on our velocity triangle at the hub station, this is what is at the hub station. Okay, if we are putting this, that's what will be giving me my 10 beta 1 as say u by Ca. If we are putting these numbers, that's what will be giving me my beta 1 to be 33.68 degree. Same way we can do our calculation at the exit of the rotor, and that's what is coming minus 27.75 degree. Now here in this case, my delta beta as we were discussing near the hub, that's what is coming to be large. This is what is a 61.43 degree. Okay. Now we can do our calculation for what will be the alpha 2 at the hub station, and that's what is coming 50.02 degree. Now in order to calculate our degree of reaction, we can do the calculation for degree of reaction, and if you look at my degree of reaction at the hub, that's what is coming 0.1. So we need to be very careful, and that's what is a flexibility we are getting when you are using Excel sheet program. If you are doing pen paper calculation, it requires a number of iteration, and it may possible you will come up with some wrong solution. So it is advisable you use your Excel sheet program, and based on that you modify your delta P0, keep on eye for your degree of reaction, keep on eye for your delta beta, keep on your eye for say your deviation angle, keep on eye for your camber angle. Be careful, this is what is very important, because there are more chances to come with say some problem near the hub region. Okay, and that too, this is what is we are configuring constant hub diameter. Okay. Now once we have done this calculation, we can have our relative velocity components at the hub station. So here if you calculate V1, that's what is coming 270.37 meter per second. Same way my V2 at the exit, that's what is coming, 254.25 meter per second. And if we look at my degree of, say, de Holler's factor, that's what is coming, 0.94. Okay, so this is what is also indicating like we are having diffusion, that's what is happening near the hub region, but you can compare these velocity components, that's what is showing like my diffusion, that's what is not happening as per our expectation in that sense. Okay. Now here for say number of blades, as we have assumed, that's what will be remaining same. So we will be taking say number of blades to be 29. We can do our calculation for pitch. This also many times we are committing mistake. We are considering pitch to be same, but we must realize my pitch, it is a function of radius. Okay, so we can do our calculation for solidity, and that's what is coming 5.012. Okay, now here in this case, let me put a comment. Say all designs what all we are discuss or we will be discussing, where we are configuring say our chord to be constant from hub to tip. But in order to manage the flow, particularly say when we say near the hub region, many times designers they are prefer to change the chord length. If we are changing our chord length, accordingly we will be having change in our camber angle. So there are many iterations people they are doing in order to manage the flow properly near the hub region. So they will be having variation of chord from say hub to tip. For many industrial designs, maybe industrial compressor as well as for industrial fans, this kind of configuration you can see. Now at the same time, suppose if we consider say we are having say exhaust fans, for those exhaust fans many times for design they are taking say chord at the tip region to be large. So those all are different design philosophies, and as I told, like with what all numbers you are playing with and ultimately what all you will be getting in sense of your final shape of the blade, just go with your computational tool and try to achieve the expected performance. Maybe at a design point, maybe at off design point, just verify with that part, and if that's what is coming as per your expectation, that's what will be your design. Okay, there are certain rules which we need to keep on eye, but at the same time superficially there is no such fixed design rule for say compressor as well as for fans. Okay, now here we will be doing our calculation for the diffusion factor, and as we know our solidity, we can say diffusion factor at the hub, that's what is coming, 0.16. So here this is what is the discussion about design method using constant hub diameter, and we have done our calculation for say the radius at hub, mid and tip station, at the exit of the stage and at the mid of the stage. Then we have started doing calculation for say mid station. We have shown the calculation at the hub station. We will see how the calculation, that's what will be proceed further for the tip station, and based on that we will be coming up with the final design sheet. That's what we will be discussing in the next lecture. Thank you very much for your kind attention. We will be discussing further comparison. We will be discussing about design calculation and the comparison of both the methods in next lecture. Thank you very much.